computer. כן. טוב, אז שלום לכולם. היום, first of all, everybody talks Hebrew? Is anybody who doesn't? אוקיי, אז אנחנו ממשיכים בעברית, ובמידת צורך גם נעבור לאנגלית. אה, היו כמה סטודנטים ששלחו בקשות לפרויקטים, אולי אנחנו נצטרך לעשות רשימה, ואני עדיין צריך להקל. מה חומר מעניין אני יכול לתת לאלה שרוצים לעשות פרויקט? בינתיים
אמ,
אני עניתי רק
סליחה,
לסטודנט אחד, כן, כן, כן.
פרויקט זה רק לתואר שני, נכון?
אם סטודנט מתקדם של תואר ראשון רוצה לעשות משהו, אה,
יש מישהו שאמר בצ'אט שהוא לא מדבר עברית, אז אולי שהיום
is,
צריך לדבר באנגלית.
is anybody who doesn't speak Hebrew? אני לא, I
Oh,
don't.
yeah, yeah. Sorry, I can't speak.
Okay, so we immediately switch to English.
Thank you.
So, uh, as I told, there might be projects. I it's not easy for me to guarantee. It's like challenge. It's first time I try, and to find interesting projects that really maybe a small research, ultimately maybe at the level of arXiv paper or even conference paper. Uh, but still, I need to think. Only one student, who it was, already came with a topic, so we started to discuss. And for others, we need to prepare a list, maybe list of students with names and emails that will allow me to contact them when, if and when I will find interesting topics for project.
Michael,
Yes.
um, so I just talked earlier, a couple of hours ago, with Roy, because I'm doing something towards my master's degree, and it is very much related. It's like optimizing a neural network, and I would love to elaborate more, but I was wondering if I should email you, because where he said it's a good idea to try and make a project about it for the course. But I'm wondering whether I could just talk to you. If you want me to email you about the details and ask you for permission or what?
Yes, you can email me, and if you are already in contact with the assistant and he is working with you, it's also okay. So you can email, say, to two of us, just
So,
for me.
so both you and Roy, because Roy helped me with this thing because he also worked on something similar a couple of years ago,
Okay,
and
very
he
good.
said that I will ask you. Okay,
Very good.
I'll email you both then.
Yes, you can email us both, and if Roy has experience and you will come up with something interesting, it's great. It's great. And if you
Okay.
will need my involvement at some point, we can
I guess I will, but
discuss.
it's still early
Yes,
days.
yes.
Okay, thank
Or
you.
even at early stage, even at early stage, is it useful? Okay.
All right.
So, how can we collect? Maybe I need a volunteer which will collect list of all participants of project. Not for me not to answer every student. It may be a bit
I
challenging.
can do that.
Okay, so you can send in chat or in WhatsApp group. Yeah, the best in WhatsApp group. Your contact and students will send you the proposals. Okay. So today Let me switch a little bit view to speaker view, multi-speaker. Okay, and I will come to slides. Where is screen sharing? Okay. Here's my picture when I was a little bit younger. That time we started recording those lectures. Actually, it was not beginning, but some important stage. So today we will try to work on derivatives of multivariate functions. And I hope very much that you already viewed the lecture. It's very important to view lecture before our meeting. Okay. And but still, the most basic things I will remind you. Let me manage a little bit my view. Okay, just a second. I need to change the view, maybe even to single speaker like this stage that you will see me. Okay. So I will remind you briefly our basic approach. First of all, we refresh the notion of the derivative, even a function of one variable. So I have a function of one variable, and I'm staying at the point x naught, and I build a linear approximation. I build a tangent line to my plot at my current point x naught. And I define differential as increment of this linear function. You see, df, differential of f, this is the same as increment of this linear function L of x. And because linear function can be generally written in this form, b plus c multiplied by increment in x, I have a linear function which has the same value as my function at point x naught, so b is f of x naught. And in order my line to be tangent, its slope should be the same as the slope of my function. So I remove this assistant height. Okay. So this is the slope of my linear function. And dl is just this c multiplied by dx, or f prime dx. Everything trivial, but it helps us to get to multidimensional function. You remember this kind of material was in supplementary short video in more clear form. And what happens in multidimensional case? I have say in this case two-dimensional plot of my function of two variables, and I stay at point x naught, and again, once again I have this tangent plane which touches plot of my function at x naught, and I want to evaluate the increment of this tangent plane when I shift, when I give increment dx to my argument. This df is increment of this linear approximation. So general expression for linear function is written here. So when x is equal x naught, again, b is just f of x naught. And what about c? C is a vector, yes? And the uh, important geometrical fact, if my hyperplane is tangent to multi-dimensional plot, so in every cross-section along every variable, I will have plot of one-dimensional function, my function of this particular variable, and cross-section of tangent plane will give me a linear function. So in this way, and the slope of this linear function will be the slope of this particular plot. And this gives us notion of partial derivative. So partial derivative of my linear function is the same of partial derivative of my nonlinear function. And this is Ci, yes, because this is expression of sum of Ci xi. And finally, I get to the expression we have in the lecture, that differential of my linear function, this is the same as dx, the C transpose multiplied by dx, and C is, like we already see, a vector of partial derivatives, which we call gradient. This gradient transpose multiplied by dx, inner product of gradient with dx. And I now will switch to general view. This is like very trivial thing, but it's important for you to get used to it. And if you have any question at this point, it's very good to ask. I even encourage you to ask questions. Is it clear what I told? It's completely clear. Is anybody
Yes.
willing to ask anything? Even stupid question. Everything is allowed here. Okay. So it's if everything is clear, or maybe yes. Okay. Okay. And now we have. Okay. Let me shrink my view and go back to. Okay. And what else we have? Okay, this is a repetition of what I already told. And we had notion of directional derivative and also notion of Hessian. So if with one variable we have function and its differential is derivative multiplied by dx, differential of derivatives is second derivative multiplied by dx. It's rather trivial. But in multi-dimensional case, we have the same structure. Hessian, this is a matrix of partial second derivatives, and differential of gradient is already this matrix H multiplied by differential of X. Here X is a vector, H is a matrix, and here is differential. Is everything clear at this point? Okay, very good. So you're good students. You watched the lecture. It's very important. Okay. Now let's move a little bit. Okay, we show it in detail in the lecture and show what is the second directional derivative. It's a very nice expression. If we have a direction r, this is this nice quadratic form, r transpose multiplied by h by r. And now the same was differential of linear operator. If something linear, this differential and increment is the same. Dy is just a multiplied by dx. And now, in order to continue, we used a very important thing that it was in second short lecture. What if I have a function of two variables, two vector variables? And just let me open everything. And I ask, can I have a simple expression for differential of my function if every variable is a function of x? And in the end of this very brief development, I get to conclusion that my differential is the same if think about one part as constant and say v as constant and u as variable, and this will be give me first part of my differential, and then vice versa. I think about v as a constant, as variable, and u as a constant, and get the second part. I hope that this development was clear enough. Do you have any questions with respect to this? I explained it briefly because it was in this short lecture. Yes.
I don't think I understood this correctly.
Yeah.
Why are we defining u of x as x and v of x as x? It could be something arbitrary like x squared with 2x minus 3 or something. Why is it x or whatever? Could be something more complicated.
Okay. It's really maybe something more complicated, but this complications is in function f itself. Say, if if I have a function where in first position I have just say x cube, if my function, maybe I should write something. Where is my writing? More. Zoom all the time. Annotate. Okay. If I have function f of x, say x plus 1 square divided by x plus 2 cube. I can approach this expression in standard form, and you probably know how to differentiate it. But alternative way would be to relate to all this part, to say this x in denominator is constant. I think about all this as constant. And only compute the differential of my f with respect to this x. You see, you have already complicated, but this x I call u, and this x I call v, and then vice versa. You will see immediately that such approach gives us a very convenient way to compute derivatives. So my rule is very simple. Think about this x as constant and differentiate with respect to this one, and then vice versa. Think about this as constant and differentiate with respect to this one, and add the results. This what this development says.
Okay,
We
thank
will
you.
see immediately an example. Uh, okay, let's. Can I capture the screen? I already forgot. Save. Oh, I don't know. Okay. I forgot if I have controls of Zoom and where I have controls of. I think this controls of Zoom. How can I remove this? Let's see. Yes. And this is remove everything. Clear all drawings. Okay. Now immediately we will see that this is useful thing. I stop my annotation. Here is a repetition of this slide, just to have it. Assume that we have a quadratic function, x transpose ax. This you already had in the lecture, but this part like gives you more motivation. How can I obtain differential of my f? I can think about x at this position as a variable, like you see it here, and on right position as a constant. So, and this will give me first term, and vice versa, you will have second term. And now you can get rearrange variables and get straightforward expression for the gradient. G of x is a plus a transpose x. Now you have this, and now maybe it's good moment to rethink it and again ask question if you feel. This is good illustration, I hope. And we will
Thank
do
you.
examples in class, and you will see the use of this again and again. Yes. Okay. Even if you have no questions, it's okay, because now we are ready to move. Let me see what. Yes. we are ready to move to our classwork. This is the main part of our class. Let's try to solve this example. Assume that I have, no, where's my pointer? Hand, yes. Assume that I have a scalar function of vector variable. How do I get it? I multiply my argument x, vector x, by matrix A. And from this, I take some scalar function of several variables of ax. And assume that for this function h, I know everything. I know its gradient, I know its Hessian. If I would have, say, h of u, let's denote this as, for example, u. Let's denote this. How can I do it in a better way? Enlarge a bit. Let's denote this part as u. So I have a gradient of h with respect to u, and I have even Hessian of h. So how do I get gradient of f of x? So if you do in the way we started, I compute differential of u. It's a multiplied by dx. Differential of h, it's gradient of h with respect to u, transpose multiplied by du. In this way, I get expression for df. If I have the expression for df as some vector transpose multiplied by dx, I know that this vector is gradient. Maybe should we start doing stop annotation. Okay. Okay. I even started it here for you because it's first time, you know. You need to get used to it. So this what I told. df is gradient of h with respect to u multiplied by du. But u is a multiplied by dx. Then du is a multiplied by dx. Can you try to substitute everything and try to get final expression? And by the way, like I told in the first meeting, everybody who presents solution gets 3 points to the final grade. So I hope it gives some motivation for you to be active.
Waiting for a solution.
Again?
Waiting for someone to give a solution now.
Yes. I expect you to solve, to write down solutions, say on your iPad or even on piece of paper. If you write on paper, then just make a picture and put in the way that we can see it on screen sharing. One of simple way is to get into your screen, yes? How you can get to your screen, I don't know, maybe even with WhatsApp, and I will give you right of screen sharing. Or if you're using iPad, you can just share your iPad.
You just send the answer in WhatsApp because I'm writing on notebook, right?
Yes. Okay. If you're already, it's great, but let us give other students some time to work. And then, what is your name again? I don't see.
Barak.
Barak. And then Barak will show us the solution. Let's give few minutes. Usually I wait till 2/3 of students are ready, or even more. You know who already solved, you can raise your hand with Zoom or with something for me to be aware. What I do, usually I turn off my microphone and my screen, my video to let you work quietly. And I even will pause the recording, but please remind me to resume recording. Okay, I now need to return fast. What Barak told us, so we already have this expression that du is a multiplied by dx. And what is differential of our expression? This is gradient of h with respect to u, inner product with u, what is written here, okay? And now we know that du is a dx. We substitute it here. And we get df, the gradient with respect to u transpose multiplied by a by dx. But we compare it with general expression that df, this is gradient of, let me undo. This is gradient of f with respect to u. Sorry, with respect to x, multiplied by dx. And if I compare those two expressions, I understand that here is gradient transpose. And if this is gradient transpose, then gradient is transpose of this. You know, to transpose the product of two matrices or matrix with vector, you just change places by add the transpose to the first place. And we get this final expression. If you want, put here u for clarity. Okay. Any question now? Is it clear? Is it more clear? Sorry, I had to repeat because I paused my recording when there was a break. And please remind me to resume recording. Okay, so very good. Now we have a 10-minute break, little bit more than 10 minutes. And at 5:30, we will get back again. I just stop pause recording. Okay, so now everybody is back. Any question about this part? Is everything clear. Okay, then I remove the writing, clear all drawings, and again stop annotate. And now let's move to Hessian, which Barak already showed, but I hope that not everybody saw his development. Let's do it independently, and if somebody else will obtain the answer, it would be great and show to us. Okay, okay. So we have already this expression for gradient. I will call it not only nabla f, but g of x. It's more convenient for me at this point. It's A transpose gradient of h with respect to its inner part. Okay, and now we need to develop a differential of gradient. Assume that we know Hessian of h itself, yes? Uh, Let me see, what do I have here? Yes, this will help us. I just remind you. The differential of gradient of h itself, it's gradient of h multiplied by du. And what is dg? From one side, it's h Hessian with respect to x multiplied by dx. On the other hand, it should be A transpose by differential of this expression. Because if we have linear function, linear mapping, yes, G is linear mapping A multiplied by something. I'm not sure how clear I am. Let me try.
Not really.
Yes. Thank you for being open. If I have G, let me write. G without argument. I will say this A transpose multiplied by nabla H. Then DG will be A transpose multiplied by differential of this nabla H. And differential of nabla H, we know this is gradient of H with respect to U, with respect to its argument, multiplied by Hessian of H. I hope that now you have everything to combine together and get expression for differential of G in terms of dx. Just think quietly, start working, ask questions at any point. You know, I even told in the first meeting that you are free to work in groups. I see now that everybody is working on his own Zoom. If you have any ideas or any other technical means to contact and work together, it's completely okay with me. If not, just interact with me. ask any question.
Whoever finished should raise his hand.
Hmm?
If I finished, should I raise my hand?
You may, yes, yes. We will wait. We will give time to other people to work quietly. Uh, at this point, before showing result, I would start open discussion. Those who didn't solve yet, maybe you have questions or anybody needs for more hints. I try to understand how many people are active among those who are without images. Okay. So, who was the second? The first was Barak. Yes, he solved both examples. And who now was the first after we started?
I was.
Huh?
I
Roy?
was. Should I share it?
Roy, you were the second
Yes.
first? The second first? Okay, I would say the bonus may give two of you. Yes, Roy, would you like? Yes, if you may share, I will stop my sharing.
Sure, for just a second.
Recording in progress.
Yeah.
Just a second.
Okay.
Okay, so it's the bottom part.
Yes. Are you able to use pointer?
Just a second.
Yes, yes.
Okay.
And how somehow you cannot enlarge. Can, is it
Yeah, I'm
possible?
using my phone. Oh, I can enlarge it
Could you
actually.
rotate your screen or something?
Let me try.
Ah, perfect. Never mind.
Only on the
Perfect.
phone. Okay, good. And still pointer is working? Okay,
Yeah.
very good. Okay.
So we want to calculate the differential of the gradient, which we already calculated in the previous section, which is A transpose del H, nabla
Just
H.
show with pointer where you are.
Yeah, I'm here.
Okay.
So A transpose is a constant, so we can take it out of the differential,
Mm-hmm.
and we get a differential of nabla H of U.
Mm-hmm.
Sorry, this is the bottom part here. Differential of nabla H.
Mm-hmm.
I'll just write this off. Oops. Okay. So it's A transpose, the differential of nabla H, which if we open it up by the law of the chain rule, so we get A transpose, the second differential or Hessian of H with respect to U, times the differential of U itself,
Yes.
which if we open it up again, we get A. So in total, we get A transpose, the Hessian of H times A.
No. You skipped. We are still
dx,
computing
sorry.
dx. Yes.
Yeah.
Should be. Du is a multiplied by dx. Are you able to write? Okay. Yes.
Wait
Okay.
just
With
a
your
second.
color, we assume this is dx. Okay.
Yep.
Yes.
So we can assume that this part is the Hessian.
So it's
The,
we say
yeah.
that dg is something multiplied by dx. So
Yeah.
something is Hessian. Okay, very good, very good. So two of you, you and Barack, may get your bonus 0.3. I ask you uh, to collect all your bonuses with current number of the question you answered. And then maybe there will be one mobile volunteer to collect everything because I really don't know how to do it in the best way. Okay, so now I will get back so you can put down all your hands and I will get back to screen sharing. Let me to screen sharing and we will get to the next share and we will get to the next problem. Oh, no.
I have a question here.
Yes, I try to see who is asking.
I am.
Tell. Okay, very good. Ask question
Uh,
is the best thing you can do in our meetings. Yes.
according to the law we saw in the tutorial about DG, when we open like when we say something is multiplied by dx, we need to put this thing in transpose, don't we?
Yes, thank you for the question. Transpose is when we're talking about gradients. Let's see the lecture.
Here the Hessian is symmetric.
Just second. You see with gradient, very good, very good. Thank you very much for your question. With gradient, differential of f is gradient transpose multiplied by dx. But with Hessian, it's just matrix of Hessian. And by the way, Hessian matrix is symmetric, so it's equal to its transpose. We are working in real numbers.
Yeah, but in the matter of the fact, there is transpose, but because it is symmetric, we just ignore it.
Uh,
Because
it's very delicate question. When we will get to Jacobian, we will get again to this point because Hessian is a particular case of Jacobian, and with Jacobian you don't need transposes. So you can remember for Hessian you don't need transpose. It's the easiest way.
Okay, thank you.
Okay. And so he is very briefly, which we saw in the answer. Okay, and now let's go to the next problem. Chain rule. we will rediscover the chain rule, which is actually more complicated in multi-dimensional case than in one-dimensional case. So we have a function h of x, which is scalar function of many variables, yes, from Rn to R. And for simplicity now, we have external function phi, which is scalar function of scalar variable. So we have this chain, yes, phi of h of x. And let's try to develop, first of all, gradient of this expression. Let me see. Okay, so again, just in two words, what will we do? We say dh is gradient of h transpose multiplied by dx, but d phi, pay attention, the phi is scalar function. It's just phi prime by differential of its argument. You don't have any vector expression. So with these two hints, you can start working on gradient. It's relatively simple, but the Hessian of this expression will be a bit more challenging. Let's start working on gradient. So who already showed answers? Barak and I don't remember. Rui?
Yes.
So Adam is the next in line?
I think so, yeah.
Yeah, okay. I stop my share. So will you share, Adam?
Yes, I'm taking a picture.
Okay. Okay, please. I don't hear you.
I'm sorry. So yeah, I started by uh, putting f, like the definition of f instead of the function itself, using the argument of phi as like a de facto argument. So I made the differential of phi, which is the
I
its
would
gradient.
no, I would use here phi prime. Here, unlike some other parts of calculus, differential and derivative or gradient are different things. So it's phi prime differential gradient of or derivative of phi by d this. Yeah.
Uh,
Can you okay? Oh, we remember if it's difficult to correct on
so
screen. Uh,
would it have been better to write it
it
as
would be
this?
phi prime. Okay, so just continue, but we remember that where you use
Okay,
defeats phi prime
so
multiplied
this would have been
by dh, yes.
dh. So this would have been h prime multiplied by dx, which would give the
Again,
gradient.
it's gradients, it's nabla h transpose multiplied by dx.
Ah,
So you
correct.
see, you did almost correct, but because of this
Yeah.
being not very accurate, you missed transposes. Okay. Yes, Adam, thank you very much. Maybe somebody
Okay.
else wants to show us more accurately. Roy or Barack or anybody else who is
I can.
okay.
Second.
Who is trying now? Roy or Barack?
Yeah.
Who? Roy. Okay. Okay.
So the differential of f using the chain rule can be broken down into phi prime of h of x, dh,
Mm-hmm.
where h is the internal function. And then using the notation of dh equal to the gradient of h transpose times dx, we
Mm-hmm.
can substitute it into the second part of the equation. Oh, sorry, I'm not with my pointer. We can substitute it right in here.
Yes.
Uh, and then we get phi prime of h times the gradient of h transpose dx.
Mm-hmm.
And then we can see we got df is equal to something times dx, so that's the gradient transpose. And to conclude, we get the transpose of what we have here is the gradient. So that's what's down here.
So it's gradient multiplied by phi prime. Okay. So actually, Adam was also correct. Yes. Sorry.
Yeah,
No transposes here. It's just gradient of inner function multiplied by phi prime. Okay. Thank you very much. You can stop sharing. Or any question? Always we should not forget other students. Any question, any comment? Okay. And now a little bit more challenging part. Here I repeat what you did. I denote this as U inner part. It's df, it's phi prime multiplied by du.
We can't see your screen.
Okay, sorry. Yeah, thank you. Just a second. Share. Okay, now you see, I hope. Do you see? Yes. Do you see my screen?
Yeah.
Okay, so it's just I repeat what other students did. So I denote this as U inner part h of x. df is phi prime multiplied by du, and du is nabla h transpose multiplied by dx. So this is gradient of f transpose. So gradient is phi prime multiplied by nabla h. Okay, and let's try to continue to Hessian. Let's see, what do I have here? So again, I repeated this expression for gradient just. Okay, here starts a more interesting thing. Gradient is some expression where x is coming in two places. Yes, here is gradient of h, which depends on x, and here is h depending on x. Very different thing. And here it will be very useful. I have a function where x is coming in two places. Then what should I say? I consider the x here, for example, is constant, and get the first part. It's phi prime. What did I write here? Can anybody explain me? What is written here? Who is volunteering to understand what I wrote here? The differential has two components.
Of total differentiation.
Differential of, I have a function I have a function where x is coming in two places, yes?
It's like the chain law.
I
Right?
have d of x, so x coming here, yeah, and so I have d g1 when this is variable, and d g2 when this x is variable and other x is constant. So but I see that I reversed order for some reason. So again, let's think that this is variable, yes? Then nabla h will also change. So it will be phi prime, I just miss here argument, multiplied by differential of this, sorry, phi prime with some small parentheses multiplied by differential of this part. And other situation when this is constant. When this is constant, it just come directly as it was. It doesn't change. But what changes is phi prime of h of x. This is the second part. I am not sure how clear I was. Let's think again. If I have h of x, some function of x, and it has also a gradient, what will be differential of gradient? It's Hessian. It's Hessian multiplied by differential of x. And what will be differential of this part? I am sorry. I really thought about this as variable and then this as variable. Change it the order. I hope that you understand the brief idea. Let me stop my annotation and try to see what is here. Okay. Now maybe it's more clear. Yes? Assume that this is variable. Let's just remove this. I need to remove everything, otherwise it will be a little bit misleading. Again, annotate, remove everything. Clear my drawing. Okay. Can anybody explain us what is written here? Here we assume that you see we have here Hessian. Then it means that we assume that this x is variable, yes? Change of gradient, differential of gradient will give us Hessian multiplied by dx. And in the second one, this is the first case. And in the second case, this x is variable. This is the second case. Are you with me?
Yes.
Who told Roy?
Yeah.
Or Roy, please explain us.
What part?
Both.
Well, we divided by the law of total differentiation, like you've written. In the first part, we have the different, like you've written it all out.
In first part, we assume that this is variable, yes?
Yeah.
So, and we need differential of the gradient in the first part. And differential of the gradient is Hessian multiplied by dx. In the second part, we need differential, we think about this as variable. And we say the differential of this expression, pay attention that here we have phi prime. So phi double prime, differential first derivative, its second derivative multiplied by this dh. If you are able to continue explore and get differential of our maybe separately, we will have two Hessians, for example. Separately get differential, get Hessian, part of Hessian corresponding to this part in order to save space of writing. And then another part of Hessian which corresponds to this. Are you able? I hope. Start thinking and say in 5 minutes we will get to some intermediate conclusion, and maybe I will leave it for your home thinking, for your thinking at home. Start working and ask questions if you will have till end of our lesson in 5 minutes. And I will stop. Okay. So we're about to finish our main part of our time. So except of two people who already solved, it's great. Do anybody else have a question or comment, or maybe you have questions or comment who raised your hands? And then we will finish and leave you for your homework to finish this part, and we will continue on our next lesson, despite that main topic will be convexity, but in the beginning we will dedicate some time to
You have just
finish.
the final answer for this question, so you can check ours.
No, we will postpone. If you will find, if you will find the answer, it's great. If not, we will continue in the beginning of next week. Okay, maybe I will even stop